Everybody knows. Yeah, so he's so kind and you give us a talk. Which title I will forget.
Written here, so
Infinitesimal braidings and Cartier by art. Yeah, it's about Cartier.
Yes, luxury. Yeah, thanks, Daniel. Yeah, let me. I'm really grateful of being here in Prague. It's my last day, and I had a really nice visit here. Hopefully, I can come back at some point. Yeah. So yeah, let me just write some things on the blackboard to motivate a little bit of what is the plan. Okay, so the starting point is a braided monoidal category. And let's say that we are working with some kind of modules. So let's say we have an algebra H, and we look at left H modules. Yeah. We would like to have some tensor product and some braiding. So this should be a braided monoidal category. And what we know is that this data is the same as having a quasi-triangular bialgebra. So it's quasi-triangular. And in this talk, I'm going to add something here. I will have some extra structure map, and this will be an infinitesimal operating. Which we will call T, and then all of this data is what is called a free Cartier. And then you might ask what you are having on the right side here, and this extra structure that you have here, be some chi, some element of H, tensor H. This is what's called an infinitesimal R minutes. Why I didn't say this is R, so this is of course an element in H. In the H with some properties, this is called the universal matrix. Okay, and then this guy here, so this data is then what we should call a free B by algebra. So just to how should one think about this chi? So I think of it as a first order deformation of some R matrix on so for the way. So let's have a look at some big R tilde that, let's say, in zero order, it's just some R. So start with one tensor one, then we're going to have higher orders, for example, some H bar chi, and so we have some higher orders, and the thing that pops up in first order, this will be this kind. Later on, we are going to ask questions like, starting from chi, can you get some R tilde? And in some cases, this will work simply as the exponential, so that you can say that by definition, your R tilde will be some R exponential that H work, like some quantization of this sort of stuff. Okay, this is just a rough picture. I think now we can start with the class.
Yeah, this elementary question. What do you mean by this equivalence?
This here?
Yeah.
Okay, so this will actually be part of the first slides. But I can say it in words here. So the thing is, if you have an algebra H, then having a tensor product and a braiding on the category of left H modules is the same as having a R on H.
So it's kind of done up a grind.
Not really. So I mean, this will be part of the slide, but I can say it here. If you start from this side, you can, by definition, say that your braiding R will be given by just flipping and multiplying with R. So this will be something like some R up acting on n tensor n. And so this gives you a braiding. And if you are here, you get your R simply as R will be sigma of H on 1 tensor 1. And you can show that this is 1-to-1.
And just one more silly question though. What do you need to remove the pre?
If you don't like the pre, you have to ask some extra properties, and this is namely a commutativity of sigma with T.
Okay.
So only in some cases this is working. Okay, maybe we can start with the slides. And I have my pointer here. Okay, yes, that's the title of the talk. I should say that this is a joint work with the Turing group. You can see the names of my friends here, and let's go to the next slides. So here, this is what a braiding is. So just a quick slide with pictures. So it's kind of, so I hope that all of you know what a monoidal category is. It's just you have some tensor product that has all the properties that you know from the tensor product like vector spaces. So it's just what you would think it is. And a braiding is then this crossing over that. So it's some linear map from n tensor n into n tensor n. So it tells you how to flip two of your objects. And the properties it has to satisfy is shown here. First two, the so-called hexagons. And this has to be written flowing down the page. So what this means is that if you want to braid M with n tensor O, this should be the same thing as first braiding M and N, and then braiding M and O. Yeah? And you have the similar rule if the tensor product is on the left side. So if this is satisfied, you can show that quantum Young-Baxter, or the braid relation holds, which is written here. So this just means that braiding M and N, so the first two, second two, first two is the same as braiding second two, first two, second two. Okay, next slide. Thank you. Right, so this was the picture here on the left side. Let's go to the right side. So what does this data mean in terms of the algebra? So if we start with a bialgebra H with coproduct delta and co-unit epsilon, then we can look at the left H modules. Category will be written like this, HM. And for this one, we get a tensor product in this way here. So I just have to tell you how is the tensor product a left module, and this can be done using the coproduct. Yeah. So by this definition here, I get a left module action on the tensor product, and this is a left action exactly because delta is an algebra map. So this is how this works. You have also an action on the monoidal unit, which is given by the co-unit. Okay. Then if and only if that I wrote here is now expressed in terms of this theorem proven in 1990 that says, okay, this category of left H modules is now braided if and only if H is quasi-triangular. So if and only if we have such an element R in H tensor H, it has to be an invertible element. I said map element, yeah, sorry. And it has to satisfy these 1, 2, 3 axioms here, where the last one simply says that the sigma that you get here will be a left linear map. And the first two, they correspond to the two hexagon axioms that we saw on the previous slide. Okay, one note that I want to make. So if you are braiding is actually a symmetry loop. So if it squares to 1, this happens exactly when R is not quasi-triangular, but triangular. So this is expressed like this. If the inverse of R is simply R of, so the tensor flip of R. That's a special case. Good, let's have a look at some examples, basic ones. So if you have co-commutativity, so if your co-product is equal to the opposite co-product, then you can take as your R matrix simply 1 tensor 1. You can see that all of what's written here, this is automatically satisfied if delta equals delta op. And this happens if you look at your algebra as the group algebra of a group or the universal enveloping algebra of a algebra. Then you can always choose this. And the braiding that you get will simply be the tensor flip. So this is like the classical situation. You can do something more non-trivial on the cyclic group. So let's have a look at the group algebra of Zn. On this one, you can have a quasi-triangular structure like this here, where the G that we have is this element of the group algebra that the power n of it is 1. And you can show that this element satisfies all of the properties. One special case that is kind of interesting is for n equal 2, because then this gives you the super geometry braiding. What this means is that this braiding will simply give you the sign that you're getting in super geometry. In this sense, you can say that super geometry is a special case of braided geometry. Okay, and the last one I want to mention is the Grünfeld double. So this you can do for any finite dimensional Hopf algebra. You can look at this guy here, so H dual tensor H. And this is quasi-triangular via this R that is just taking a basis EI and a dual basis EI. Next slide, please. Okay, this was all the known theory. Let's do something new. So here I've written the R tilde that you have also seen on the blackboard. So let's explain a bit what is going to happen here. First of all, we start with a bialgebra H, and we look at the corresponding topological bialgebra H tilde, which is just H in formal power series. And you extend the coproduct and co-unit and everything just in the trivial H-bar linear way. And so this gives you something that's called a topological bialgebra. And let's say that you have an R matrix, R tilde, on this H tilde. What you can do is you can look at R tilde in 0 order of H bar, and you can show that what you get there, this we call R, this is automatically a quasi-triangular structure for H. So since this is automatically an invertible element, you can factorize R out and expand R tilde in this way. So this will start with 1 tensor 1 plus something plus higher orders. And what you have in first order, you simply read the axioms of R tilde, and this will give you the definition of what an infinitesimal R matrix is. So this is how we found this definition. And so let's spell it out. It's written here. So we call this triple HR chi pre-Cartier bialgebra if HR is quasi-triangular and chi is an element of H tensor H. Yeah, first of all, it has this commutativity with the coproduct, so I can move it to the other side. And then those two extra axioms here that looks like some kind of braided version of a primitive element. Yeah? So you apply the coproduct to one of the tensor legs and you're getting 2 terms. Here, just to clarify, this chi 1, 2 is just chi tensor 1, since here we are in the 3rd tensor power. So I just have to specify where the chi is placed. In a similar way, you have here the chi 1, 3 just means that the first leg of chi is in the first tensor factor and the second one in the 3rd. And in the middle, there's just 1. Okay, that's just definition, very well. And then you can either make this into a proposition or into a proposition by definition. It's just saying, just looking what we are having on this side here on the level of modules. And then this chi corresponds to a natural transformation T, which satisfies those two axioms here, which just correspond to those. And the first one is just telling you that T is a morphism of left H modules. If you ask something more, namely that R chi is the same as chi of R, then we call the triple even a Cartier bialgebra. This is how you get rid of the pre, yeah. And on the level of modules, this corresponds to sigma co-muting with T. So I can move it to the other side. Okay, I think this is what I wanted to say here. Excellent, thank you. With some comments on the definition, part of this was known, namely this special case. That's why we called it Cartier. So in the symmetric case, if our braiding is not a general braiding, but just a symmetry squaring to 1, yeah, and we are asked also this axiom here, then what we get is a definition of Cartier category, which was introduced here in this paper. And you can find it also in the book of Kassel. It's written down quite nicely and more recently in his preprint here by those two guys. And that, yeah, since we are more general, so we can do things in general braided categories, not only in the symmetric ones. We are using this pre to say, yeah, it's slightly weaker. One more thing, the chi's form a vector space, and what this also means is that 0 is always a possible infinitesimal R matrix. Okay, maybe here's some comments. So in the, let's say, classical setting, when your algebra is commutative, you can show that the axioms of chi boil down to say that chi is in primitive tensor primitive. And okay, speak is symmetric if you want to even the special case. Okay, some example. If you have so this triple here, a quasi-triangular Lie bialgebra. I don't give the definition, but what this means is basically just a Lie algebra with a co-bracket, and this co-bracket is induced from an element small r, so from what is called a classical R matrix. In this setting that is studied very well by many people, you can get a chi by taking the sum of R and R op. And this will give you an infinitesimal R matrix for the Hopf algebra UG with the trivial R matrix 1 tensor 1. So that's one special case that we get. Something less trivial is here for Sweetler's Hopf algebra, which works like this. So here you take the algebra generated by some g and x with the rules that g squares to 1, x squares to 0, and xg is minus gx. You have these co-products, so this tells you that g is group-like and that x is kind of primitive, not really primitive. You have this x and g here, and also the antipode, but I don't even write it down. For this Hopf algebra, you can find an R that I wrote here with some index 0 for a reason that I'm going to tell you, and simply like this. So it's 0 because you can actually classify all possible R's on Sweetler's Hopf algebra, and for this one you will have some extra terms in X here. But if you set one of the parameters to 0, you will just get this. Let's stay with this easy case because okay. Well, and for those guys, we can find some non-trivial chi's, and we even classify them. So all possible chi's are of this form here. Okay, one more proposition that might be interesting is that if you have such a triple that is a pre-Cartier bialgebra, and you have a Grünfeld twist, you can twist everything. So you twist the Hopf algebra, you twist the R matrix in this way, and you twist the chi. Then what you get is a pre-Cartier bialgebra. So this works very well with this. Okay, next. That's a question.
Yeah, so is there a more or less nature of a bracket that one can define from the space for infinitesimal matrices?
That's an excellent question. That's something we try to do, but it's not that easy because it's not clear, let's say, apart from the classical algebra setting, what a Lie bracket should be, right? It's not clear what are the axioms. But it's something we are aiming for. Use kind of this, if you go back to the definition of the chi, is here. So here I understand this as a kind of Leibniz rule. I get two terms, and a Lie bracket is also okay. I cannot really make it precise now, but I mean the secret motivation is also to understand this in a way as a braided version of a Lie bracket, but we are not there yet, so I cannot make some interesting comment. So can you go back to the new one? Okay, so let's have this first. It's a non-trivial theorem that we proved. So if you take a triple as in the previous slide, then you can show that the chi is automatically a Hochschild-2 cocycle, which means that it satisfies this equation here. And you can show that chi satisfies what we call the infinitesimal quantum Yang-Baxter that looks quite like Yang-Baxter, just more terms. And yes, you can see basically in each of those terms you have 3 R's and 1 chi, and the chi is like shifted through, and you show that this holds. And part of this, for the special case of the universal enveloping algebra of a quasi-triangular bialgebra, was proven by Shan in this paper. But if you take this sum of R with R op, and that is a 2 cocycle, this was proven by Shan in 1997. But of course, here we have a much more general setting. It's not just a trivial braiding, it's any braiding. One more thing that we can realize is that if you have a Hopf algebra, so even an antipode, you take a chi, you write the 2 tensor legs like this, so as a finite sum. You apply the antipode to the first one and you multiply, so you get something in H. And you can show that this element gamma here is always in the center of the Hopf algebra. So it's a way to get something in the center. We call this the Casimir of H. What you can show that in the Cartier triangular Hopf case, you can show that chi is not only a cocycle but even a coboundary. So here you can even explicitly write down that chi is given as the image under this Casimir element under the Hochschild differential. Just so you know, it's written here. So what this tells us is the difference of pre-Cartier to Cartier is kind of being a cocycle or a coboundary. It makes sense, right? Okay, next slide, please. Good. So this was the story for modules. If you don't like modules, but you rather work with co-modules, then you can formulate everything with co-modules. So for a algebra, I write this with the upper H, is the category of right H co-modules. So a co-module, just in case you don't know, is just a vector space with some linear map that is dual to the action. So here, this is what I would write like delta n. So this takes one element and gives you something in this tensor product of n with h, and it satisfies the dual axioms of a module. Also for this, you can prove a similar theorem that says the category of right H comodules is braided if and only if you have a universal R form, so not an R matrix, but R form now. So that's a linear map from H tensor H to K, satisfies some axioms here. It's just the dual ones of the universal R matrix. And in this case, the braiding that you get is of course now using the coactions and this R matrix. So this is how the braiding looks like. And so in this setting, we can say what an infinitesimal R form is. This will now just be some, so here's the definition. This will be given a co-quasi triangular bialgebra. Here co just means, okay, this is for the R form. You take a chi that is now a linear map from H tensor H to K, satisfying those axioms here, which are really just the dual ones we've seen for the modules. And then we also call this pre-Cartier co-quasi-triangular bialgebra. Everything that I said about co-cycles and co-boundaries also works in this dual setting. It's really just the same thing with reversed arrows. Okay, next slide, please. So maybe some example that is less trivial. Let's have a look at quantum 2x2 matrices. So take Q, just a complex number, should maybe not be 0. Then MQ2 is the free algebra generated by some alpha, beta, gamma, delta modulo Delmani relations that are written here. So basically just some Q commutativity. Beta and gamma like each other, alpha and delta hate each other. That's something complicated here. And for this one, so this turns out to be a bialgebra with coproduct written here as the matrix co-multiplication and co-unit like this. So in case you don't know this, so this co-multiplication really just means that, let's say, the delta of alpha is just alpha tensor alpha plus beta tensor gamma. So it's going like this and then down. Okay. Very well. For this guy, you have an R form. So this is now a linear map, as we've seen, from H tensor H into K, or into C in this case, which is given on generators like this. So it's mostly 0, but it's some cases not. And okay, it is known that this gives you a co-quasi-triangular bialgebra. What we showed is that you can also get an infinitesimal R form here that we call partial Q, tensor partial Q. And this even makes this tuple into a Cartier bialgebra. So you have this extra commutativity of R with chi. So I should tell you what this partial Q is. It's rather simple. It just takes an element psi and maps it to epsilon psi, where we multiply here with the degree of psi. So you can show that it even satisfies the Leibniz rule and is a central element. Okay, next slide. Good, so if we have the 2x2 matrices, let's go to GLQ and SLQ and check if the same trick works here also. So pretty sure that you know, but just to explain what this is. So you take a look at the quantum determinant that is like this, so just alpha delta minus Q beta gamma. And you say GLQ2 is just MQ2 with an extra generator theta that you say has to be the inverse of the determinant. And for SLQ2, you set theta to 1. You can show that GLQ2 and SLQ2 are automatically co-quasi-triangular algebras with the bialgebra structure and R coming from the ones of MQ that we've seen on the previous slide. And what we try to do now is to extend this partial Q that gave us our chi to GLQ2. And this can be done simply by setting it on theta to the power n. We set it to be minus 2n. And it turns out that this is the right choice. So this works and also gives you an infinitesimal R form on GLQ2. Now there's a problem, or not a problem, but something that we realized is that this does not work for SLQ2. So if you want to see if the same chi goes to SLQ2, you see it doesn't work, and you get some inconsistency here. So this does not descend to SRQ2, and we could even show that there is absolutely no non-trivial infinitesimal, should be art form, not braiding, sorry, on SRQ2. And we don't really understand what this means. So this is basically telling something that it is not possible to take a first order deformation of the braiding of SRQ2. But I don't know what is the reason behind it. Anyway, next slide, please. Okay, to understand this a little bit better, okay, what I'm going to show is that we can find a lot of examples of our triples using something that's called FRT. And okay, let me walk you through the way this is done. Okay, what FRT does, it starts with a braided vector space, and from this braided vector space, it gives you a co-quasi-triangular bialgebra. So what we did, we gave a definition of what is an infinitesimally braided vector space, from which we will give you a pre-Cartier bialgebra. So this is first a classical picture, and then I will give the extra data. So first of all, a braided vector space is just a vector space V, and C is an endomorphism of V tensor V satisfying the braid relations. So in the finite dimensional case, we can choose a basis V1 to Vn of V, and have a look at this, the set of some indeterminants T with upper and lower index that runs from 1 to capital N. And this free algebra then is automatically a bialgebra, where we just take the usual matrix quantum group coproduct and the co-unit that is basically just the Kronecker delta. So now, since we have this method C, take the coefficients of C. So this just means on this basis, I can expand C like this. I get some scalars C with 4 indices. And then I take the two-sided ideal IC in the free algebra, generated by those guys here. Or here you can see we sum over M and N. And it turns out that the quotient that you have here is a bialgebra. So this works. And you can even have a coaction, but okay, it's not very important here. And then what was shown by those 3 gentlemen here is that for each finite dimensional braided vector space, there is one and only one co-quasi-triangular structure R on this quotient, which on generators is given by the scalars, the coefficients of C. So this is the way how to get the co-quasi-triangular bialgebra from the braided vector space. Next slide, please. Okay, now the infinitesimal version. So we call this triple ECT an infinitesimally braided vector space if we have a braided vector space, let's say finite dimensional, and an extra endomorphism T, also from V tensor V, satisfying this 1 and 2. And this looks a bit complicated, but it's actually doable to figure out in some places that this works well. First, so if you go back to, let's say, the easy case when C is just a tensor flip, you can see that 1 is empty, so it's automatically satisfied. And 2 gives you something that is known in the literature as the infinitesimal pure braid relation. Those guys were studied by Ono, and there is a connection to Ettinghoff-Kashtan quantization, and so those guys are very famous in the literature. But here, for us, of course, this definition is much more general. We can take any braided vector space, and this will give you something. Okay, if you just have any braided vector space, you can also solve 1 and 2 if you take as T multiple of the identity. This is a way to solve this in a kind of trivial way. And also, if you have a gradient that is of this special type where you just flip the base elements and you multiply by some non-zero number, we classify all possible endomorphisms T satisfying 1 and 2. So we have some non-trivial examples where this is meaningful. So this definition is not empty. It's next slide. This question.
Yeah, so it seems plausible that we can have a direct sum of two infinitesimally braided vector spaces. So is there something to say about something that we can call irreducible infinitesimally braided vector spaces, the ones which we cannot decompose into a direct sum? Or also indecomposable in this case?
We didn't think about it. I cannot answer this. Sorry.
And also probably one can also for the tensor product actually.
For the tensor product, we have something. Yes. So this. I mean, I didn't include this as a slide, but you can show that. Yeah, the tensor product. Yeah, you can simply take the sum of the two, and this will give you a T. Okay, so this was the definition of this infinitesimal braided vector space. Now we can use this to go from the quotient that we've seen in FRT to a double quotient. So if you have this beta VCT, you take as your T with the 4 indices, the coefficients of T, and you take the two-sided ideal IT in AC generated by those guys. So it looks just like on the previous slide, with the difference that here we don't have the small c's, but the small t's. You take the double quotient, and what we showed is, first of all, you get a bialgebra. Secondly, your R form descends to this double quotient, so you still have a co-quasi-triangular bialgebra. And furthermore, you have a chi given by the small t's. So yeah, this is the theorem giving an infinitesimal braided vector space, you get a pre-Cartier co-quasi-triangular bialgebra. And so if you take this trivial solution, meaning that you take ST just the multiple of the identity, then the chi's that you get are not 0, but they will be like this. So just like a multiple of the co-unit. And for example, this is how we came up with the example of MQ2. This is just coming from this special case that is automatically solving this 1 and 2 we had on the previous slide. We have also a way to go back. So the other implication says that if you have a pre-Cartier co-quasi-triangular bialgebra, HRT, and a left H comodule V, then you can structure this as an infinitesimally braided vector space by making this definition. So your endomorphism C is basically just given by R. Now we have some flip here, and your T is given by pi. So this is the other implication. Okay, next slide. By the way, how am I doing with time? Am I super fine? Yeah, because you can see it's approaching the end, so it's okay. Very good. So one more thing that we showed is some Tanaka-Klein theorem for our setting. So let's first state a classical theorem that says, so if you have a braided monoidal category and a strong monoidal functor to finite dimensional vector spaces, then you can actually understand your category C somehow as the category of comodules for some co-quasi-triangular bialgebra. So what this means is, in this setting, you can find a co-quasi-triangular bialgebra, HR, and a strong braided monoidal functor, capital omega, such that you have this diagram here. So really saying that we know that starting from this data, the picture for the comodules, you have a braiding, but this tells you that kind of all braided monoidal categories that are nice can be seen as a category of comodules over some co-quadrangular bialgebra. So what we showed is that if you do not only have a braided monoid category, but even a pre-Cartier braided monoid category, then the bialgebra that you get has this extra chi. So you get it back, and the proof is like sketched here. It's not very complicated, but maybe I can skip this and just the last slide. Yeah, so as something that we are having in mind, so this is work in progress, is also something I mentioned on the blackboard. So we have seen that kind of the motivation for the axioms of chi was you take the trivial topological bialgebra of formal power series here. You take an R matrix, R tilde, on this H tilde, and you look at the first order, this gives you the chi. Now you can ask, can I go back? So just given H R chi, can I find an R tilde that is quantizing my chi? And so this gives us a kind of a natural quantization problem. And we are not able to solve this in general, just in some baby cases. One of them is for Sweeler's Hopf algebra that we've seen on one of the first slides. So we classified all the R's and all the chi's, and you can show that if you do this trick, you simply take the exponential of your chi, which in this case is not really an exponential, because you can see actually this is just the first term and then the linear term, and then all the higher orders vanish automatically. But you can show that this guy that you get here is actually a quasi-triangular structure on your formal power series. And what we try to understand is what this means actually. So is this some kind of quantization of your bialgebra that you are getting here? The thing is that there should be some relation with the Ettinger-Kashta quantization of quasi-triangular Lie bialgebras, because in this case, what they showed is that if you start with such a small r, you can find, so here you know that your chi is basically the small r in this case. Your r here is just 1 tensor 1, so you have just this term on the right side, and they can quantize this, so they can give you the r tilde, but only in this setting here. And what we are trying to understand is if there's a way to have a similar quantization theorem also in this more general setting. Okay, and I think this was everything I wanted to say. Thanks for your attention.
Thank you. Guys, questions?
Not really a question. Could you go back to the example of the figure 2 quantum matrices? Just curious.
Let's see if I can go back. Yeah.
Yeah, there.
Mm-hmm. You're looking for the chi, or yeah. So here it's really basically the epsilon, so the co-unit that you're using, but you are multiplying it with the degree of your element. So what the general formula is we have seen in this FRT. It's here. So if you plug in something like this here, you get some scale factors and then your epsilon. And so this works for all FRT bialgebras. You can use this as an infinitesimal R form.
And sorry, or n and n are
Degree of the, so here you can see I have m entries here, generators, and here I have n. So that's why it's m times n. And the lambda is just a scale factor that you can always use, since you know that, yeah, since you have a vector space, you can always scale things, and that's the work.
so morally it's these guys are something constructed out of the co-unit.
In this case, yeah, but it's if you go back to the braided vector spaces, this corresponds to kind of the trivial way. So this T is just multiplying the unit basically. So the trivial way to solve this 1 and 2. If you can figure out something that's non-trivial, then probably expression of chi will be less nice. But in principle, every t that solves this will give you a chi.
Unmet basis and this event is there good, for example, for integrable systems.
So this is a good question. So of course we know that if you have a big R matrix and a small R matrix we have seen for the universal envelope algebra, this has definitely some relevance for integrable systems. Our chi's are kind of more general classical R matrices, but I have no clue if there's any application in integrable systems. For this, I don't know enough about this subject. But yeah, like maybe there's a way to make it work. And for this, I guess this question that you had, one needs to understand, yeah, what is a quantum Lie algebra, and then maybe a quantum Lie algebra with this chi can be something that has a meaning in integral systems. But I don't know. It's just guessing.
So if you go very vector space, then you can ask for from and make it out.
Mhm.
You mentioned so that just gives you I can go earlier on.
Mhm.
So then if you've got the extra structure, the infinitesimal very vector space, what does that do with the negative value?
I don't know. So what could it do? I mean, maybe if you could, if you solve this condensation question so that from the infinitesimal braiding, you get a deformation of your braiding and then even a braiding from the power series, then maybe you get a quantization of the Nichols algebra in some sense, but I don't even know what it means to quantize a Nichols algebra. So it's
Start to use a simple example, we got 3 as a braiding, does it come into this conversion?
yeah, for the flip, we have seen yeah, so this basically corresponds to the commutative case. Because there, yes, you can take your R matrix as 1 tensor 1, yeah. So the corresponding braiding is the flip, yeah. And for this, you see that the axioms that you have here, so if the R is just 1 tensor 1, you see what's written here is really just that chi is primitive in both entries. So it's something primitive tensor primitive. And so it's basically saying that you have something like a small R matrix, right? Because so in case you have some Lie algebra in the background, this just tells you that it should be a small R matrix. But then of course it's not clear even in this easy case how to quantize this thing. So you have just the first order deformation of the flip, but I don't know what the higher orders are. Yeah.
Okay, so R matrix, does it go on your big?
Hätte noch verstanden und dann.
Not necessarily. Speaking more about you have 3 when you going back to race question, you have 3 on other space, you can define 2 Nichols algebras, exterior and symmetric.
Mhm.
Then if you have some R matrix coming from your Lie algebra, you can define a Poisson bracket but not by taking some as O, but you take a minus. So R matrix minus O. Well, it's not necessarily open bracket because half bracket also this game sometimes doesn't vanish, but if it's vanish, have a Poisson structure and you quantize your favorite information translation.
Plus, if you Heisenberg, right?
So if you have R plus R op,
Yeah. I mean,
Plus-
that's.
okay, okay. I don't know, but so what?
And it's a module for. No. If I, well,
So I just know that so this, if you sum them in this way, what you get is definitely a Hochschild co-cycle. That's something that we showed. Yeah.
I think I've seen some. In some extent.
Quite possible. Yeah.
Severus Fantastic.
Ah, okay.
But yeah, I might not remember correctly. It was 30 years ago.
Yeah, I mean, if you have a good reference where something similar is done, it's
Well, I just remember this. Talking about sum and difference, and one way getting the green for double and the other one, like the model.
because we really thought that what we are doing here is something rather natural. It's really just looking at the first order of an R matrix, and we were quite baffled that no one else did it, at least in this general setting. I mean, what most people do is looking at in the Lie algebra case, if you have the universal enveloping algebra and you take R as 1 tensor 1, this happens. So I mean, there's literature on this, but for the general case, we didn't find anything. So it was quite natural to
So
write this
I
paper.
think also you could add, if you like, this spectral parameters, young bacterizations.
So I don't know if I want to do that. Yeah, it's but yeah, it could be
Because then you have also classification, right? You know, like the laminate, the classical array, this is even the only rational,
right. There was something there.
LHD and trigonometric.
Okay. Yeah, maybe we should look at this. Yeah, could be interesting.
If there are no questions, then yeah, then. Being a good companion through some evenings.
Yeah, it was a great time here.
Yeah, hopefully I'll take for longer.
If the gacha is merciful, then okay, stop recording.
Then we can discuss.